On page 3 of Unit 7 notes, let's look at the examples that are midway through the page first. So we want to find the magnitude and direction of each of these vectors. I have a vector u that is in its rectangular or component form is the vector 3, 2, versus a vector v that in rectangular or component form is negative 2, negative 5. So I drew the vector first of all in standard position. So the tail of the vector had to go at 0, 0, and the head would go at the point 3, 2. And to find the magnitude and direction for the vector, I know I can use Pythagorean theorem to determine the length of that vector. And then to determine what the angle is, I'm finding this acute angle in this little right triangle here. And so I know that the opposite over adjacent of angle theta that I've marked here is 2 over 3. If I take the inverse tan of 2 over 3, I got an angle of 33.7. Now, if I asked you to give me the magnitude and direction, I probably would say something a little more about the direction if this were on a test or a quiz, and I would ask you to give me the direction in terms of a standard position angle or as a bearing. Now, if I asked for you to give the angle as a standard position angle, we would want this angle theta, which is 33.7 degrees from the positive x-axis. So one form of the vector is to write it in the polar form, and polar form will have the magnitude and the direction listed as an angle from the positive x-axis, as you're accustomed to using for an angle. So this would be our polar form of the vector. The common form would be probably more in the context if I were dealing with something that was an aviation type question where I want to know what the bearing is as the angle. And so to find the common form of the vector, I likewise have the magnitude as square root of 13. However, now I want to list the angle as a bearing, and the bearing is always from north measured clockwise. So if I know this angle is 33.7, I know its complement is 56.3 degrees. So I know how to write the rectangular or component form of the vector is 3, 2 with the arrowheads or the pointy parentheses. And then two other ways would be to use the polar form or common form. And in either of these cases, or any of these cases, we always use the arrowheads at each end to denote we have a vector. It's just a matter of whether we have the horizontal, then vertical movement, or whether we have magnitude and direction. Now I showed a second example over here with vector v. And vector v, I move component form or rectangular form. I move left and down. I drew the vector in standard position just because of ease of working with a vector when it's written in that form. And so I can determine the magnitude of the vector with Pythagorean theorem. Magnitude is always positive. It doesn't matter what quadrant you're in. You just want the length of the vector. And then I'm going to neglect the negatives on these when I determine what the angle is. I'm actually just going to find this little acute angle that this reference angle, as we referred to before. But I'm going to use this little angle, this acute angle, as the reference that I'm going to find. So I'm going to disregard the negatives on the 2 and the 5 when I actually come up with what this angle is. So in my little reference triangle here, I know that the x component is 2, or absolute value of it is 2, and the absolute value of the distance down is 5. So opposite over adjacent tells me that the tangent of the angle is 5/2. Inverse tanning, I get this little acute angle here that it makes with the x-axis is 68.2 degrees. Now, depending on how I give you directions as far as which form of the vector I want you to put it in, say I ask for you to give it to me in polar form. Well, polar form, I give the magnitude, which we had already determined is a square root of 29, and then I need to give its angle as a standard position angle, which if I take 180 degrees and add on this little acute angle that I already found, I would be at the 248.2 degrees. I could likewise list this standard position angle as a negative angle if I had wanted, and take 180 degrees less this and have it be a negative angle here. But I'll stick with it in the kind of normal notation of going in the counterclockwise direction for that standard position angle. Now, if you were asked for directions to have this changed into a common form vector, once again we need the magnitude of the vector here, and then we're going to need the angle but referenced from north and going clockwise. So I can do a couple different things. I can either take and rotate around and say all the way to here is 270 degrees, 90 plus 90 plus 90, and then I am shy of that by this theta, so take the 270 degrees less the 68.2 degrees, and that would help me find this angle. Or, if I know that's 68.2 degrees, I could find the complement and find this little portion of the angle here and take 180 degrees plus that little portion, and in either case you'd end up with 201.8 degrees. So if you are asked to find a polar or common form vector, in either case you have to find the magnitude, and you'll have to do some type of finding a little angle that the vector is making with the x-axis, and then you'll have to look at the picture basically to determine whether what you do in order to turn it into a standard position angle or into a bearing, which is referenced from north. But always start by drawing a picture. Now, secondly, we need to look at what does it mean when we are doing addition or scalar multiplication on a vector. So let's go back up to the top of this sheet. And if I have two vectors, here's my first vector u, and here's its components, and I have a vector v, and I have it in component form, it's actually very easy to add two vectors if I have them in component form. If I have them in component form, all I have to do is add the x components and add the y components, and I'll have my new resultant vector. Now, what are you really finding when you find that resultant vector? Well, picture-wise, we showed it down here. If I drew in vector u, moving u1 over and u2 up, assuming these are two positive numbers just for the sake of argument, and then draw in my vector, here would be vector u. And if I'm adding two vectors, the notation or the wording that we say is we always add vectors head to tail. So if my first vector was u, I would graph it, usually put it in standard position. It's just easiest to have this reference point be 0, 0 to begin with. And now, when I add on vector v, I have to move the tail of vector v right at the head of u. And then this would mean that I would be going the components of the v vector and say both these coordinates again are, well, just to say for the sake of argument, are positive. So I would be moving over v1 and up v2 to get to the head of my vector v. So I graph one vector, I plot the other vector with its tail at the head of the previous one, and then literally the resultant vector is from the start point to the end point. This is our resultant vector. So when we add two vectors, we will get a new vector, and it really will be basically from the start of one to the end of the other when they're added head to tail. Now, picture-wise, we have some commutative property for vectors that if you add vector u plus v versus vector v and then plus u, picture-wise, your resultant vector, or the sum of those two, will be the same. So you can actually add them in either order. Now, another thing to look at is what does it mean if we put a number outside in front? And the algebra of it is very easy when the vector is in component form. If I put a number in front, for instance, if I had 3 times, say, vector 2, 5, that would mean this is a vector that if we start at a position and we go over 2 and up 5 to get this vector, so this is 2 and this is 5, there's our vector 2, 5, put in standard position, that if we have a 3 out in front, we really want the vector to be lengthwise 3 times longer. So it's kind of like taking 3 of these and just extend the magnitude of the vector in the same direction 3 times longer. Now this can be done very, very easily by it almost looks like a distributive process. If this vector is in component or rectangular form, this would just become 6, 15, or the new vector 6, 15 would be the equivalent to this 3 times vector 2, 2, 5. So the mathematics of that are quite similar to a distributive property. Now, gave a little example down here on the bottom that if I had my vectors u and v, if I wanted to add vector u plus v together, I started out graphing u, which was over 3 and up 2 from the previous example, and then when I add v to that, from the head of this vector, that's my new reference or my new initial point, and I need to move -2, -5. So I moved -2, -5. So here's the tail of u and its head. Here's the tail of v and then its head. The sum of these two, which is called the resultant vector, is from the tail of the first vector to the head of the second vector, and I've made it very dark. So this resultant is the u plus v vector. Mathematically, very easy to find this resultant sum. I add the x components to get 1. I add the y components to get the y component of my resultant vector. And we can see that if you go over 1 and down 3, that the mathematics actually matches with our picture. Now, if I have something like this, a u minus v, this means the u vector is this 3, 3, 2 vector. A negative v means that your vector is actually going to go in the opposite direction. So if I had a vector that was going at, cover this up a second, if I had a vector v, as up here, that is going to the left and down, negative v would actually go the opposite and would go 2 and 5. So it is kind of like you're distributing through a -1 to both these components, and it will mean the vector, this vector goes left and down, and this is vector v, and vector -v will go +2 and up 5. It will be the same length, however it will go in the opposite direction. They would be parallel to each other. So I did the mathematics of this up here. I have u as in its component form 3, 2, and I found what -v was, which is the vector 2, 5, and now I'm adding these two together. I draw u, I attach to it the -v vector, which is now over 2 and up 5, and then this is my resultant vector from, again, the tail of the original vector to the head of the last vector. And I get 5, 7, and from my picture, over 5 up 7 does make sense. So we're done with page 3.